Hi, good afternoon, good evening, or good morning, wherever you are. Welcome to SETI Live. Feel free to share in the chat where you're coming from today, where you're watching us. I'm Pamela Harmon. I'm the Director of Education at the SETI Institute, and it's my pleasure today to have a conversation with Dr. Mojgan Hanekar, who's an affiliate and colleague in the Center for Education. She has a PhD in physics from Kansas State University. Dissertation was exploring students' patterns of reasoning. She has a master's in physics and a master's in astronomy education, where she researched understanding and accessibility in physics. Her research interests include three realms of cyber learning. One is visualizing scientific communications. She's also interested in multidisciplinary undergraduate research and, in general, global education, outreach, and communications. She's been on the faculty at SUNY Polytechnic University and at St. Francis College. When she was at SUNY Poly, she was a professor in media design for visualizing physics. She's also a published author. She's recently published Visualizing Dynamic Systems. She's written 4 proposals this year for the SETI Institute, and she is our guest panelist this afternoon. So welcome, Mojgan. It's great to see you in the ether again. Hopefully we'll get to see each other in person soon. My first question for you is, what sparked your interest in this field? You're interested in physics, astronomy, visualization, or was there a moment or an experience that sent you down this path?
Thank you so much for inviting me today. I'm so honored to be in this session. In general, I was impressed to know how nature works, so how this is brought me to the path of physics. But particularly about this research, in fact, the content of this book, what brought me to this was that teaching science is purely abstract, and with many of the teaching methods from physics education research, I often implemented, making so many opportunities for visualization for students, but most of those things was not scalable. It was just 1 or 2 experiments that I could build with the help of other technicians in the class. But when I went to so many of these conferences, when I take conferences, I noticed that emerging technology can help us. With the help of advanced technology, we can make so many of these experiments scalable in a large scale and make it available to many students.
Yeah. Thank you. So shout out to listeners and viewers from across the US and Florida, Texas, your old stomping grounds, New York, California, Georgia, and we have some international visitors from Australia. So why did you write the book? What did you want to accomplish by, publishing this book?
In 2019, I was invited a speaker in American Association of Physics Teachers. I usually attend that conference, and a publisher heard about my talk, and they invited me to write this book, and I thought this is a great opportunity. So because it was a while I was working on this research that how we can implement emerging technologies in visualization in scientific communication. So that was a good opportunity for me to do that.
Yeah, well, congratulations again on publishing the book. I've read the book, and and we've worked together for almost a year, and I'm aware that you're interested in education and communication of science concepts, both. And, I found it fascinating that one of your science education citations is over 100 years old. I was a science and math high school teacher a few decades ago, and when I taught, I was, I was a firm follower of the National Science Education Standards at the time and the AAAS benchmarks for science literacy. And both of those publications emphasize science as inquiry, learning science as a process. Science is not memorization. And here we are, John Dewey wrote that paper in 1910, over 100 years ago. I was in the classroom over 20 years ago. Why do you think we're still in this transition? Why is it taking us so long to get from inquiry and process to get to that instead of memorization?
There are two types of barriers to that. One is implementation barriers, that is lack of resources, or some things like the experimentations are not available for many reasons. Some of these abstract concepts, it is hard to do experimentation. This is why we want to use emerging technologies. Another barrier is mostly attitude barriers, and that emerges from the fact that when students go through inquiry teaching, they need to face cognitive dissonance, and a student's metacognitive knowledge is not to that level to understand that metacognitive is a good thing to happen. So they think that they are not understanding, so they resist. And unfortunately, where they resist, many also educational system just go with what the students are, and then they don't go there. And that is the attitudinal problem that we need to address. And I think from early on, we need to embrace that failure is good. We need to explore, and if you fail, it is not a bad thing. If you go to cognitive dissonance, it is good, and we need to change our assessment system, which hasn't been done, based on how much a student think, not how much they are correct. So that is the big change that should happen in our assessment. Also, evaluation of faculty should be at how much they implement the research, not just the way that they evaluate faculty or teachers is that how much the parents are happy or students happy. So those are the things that are attitudinal problems that hasn't been resolved in this.
Yeah,
and we haven't accomplished that.
Yeah, this is big change, and it was called for 100 years ago, and we're still just making small increments towards that change. And working with you and other people at the Institute, we are certainly aware that emerging technologies can be employed in communication and education to make those changes. You mentioned cognitive dissonance, and for anyone who's watching who's not an educator, cognitive dissonance is when you're uncomfortable, when you're uncomfortable. And as a learner, as a student, this can be horrible because you feel like you're not doing the right thing. And this is important for students and teachers to understand. In my teaching experience in a high school, when students were having cognitive dissonance, they might be more loud. They might, be frustrated. And if an administrator walked by and looked in my classroom at that particular moment, they might have thought I was a horrible teacher, when in fact I was doing the best teaching possible. Yeah. Let's see. So would you like to share some images where you can illustrate how systems, how unseeable systems or complex systems can be depicted, and the power of visualization in communication and education?
Sure, I share my screen here. So in my book, I discussed about complex systems, and that is because most of the science is about complex systems and categorize different type of systems. So you have systems that are simple, deterministic, like if you want to define the motion of the planets in a solar system, that is a deterministic thing that you can find it with equations. So any time-dependent system, you can describe it with a differential equation, or you can describe it as iterations of the functions. That will lead to fractals. So it is very important to know when you're talking about system, which type of this it is. And during the years when it evolved, the science, the cognitive process of the scientists and people who learn it also evolved, because learning is that you create a mental model of the interrelationship of the concepts or entities in a system. When you find a model in your mind that how that works, that means you learned it. So you bring an equivalent cognitive model of that. And during the years, this evolved as scientists find different models, like they have a new methods of the in fact, a statistical way to solve, or mathematical model, or quantum mechanic, that is probabilistic thinking. All those just evolve different type of thinking, and dynamic thinking is different from a statistic thinking. So I give this explanation because these images I'm sharing with you, they are fractals. And fractals, mostly they are showing chaotic behavior, and they didn't know these patterns until Mandelbrot. He used a computer and just graphed these things. This particular image you see here is three pendulums that are in fact magnets, and they are attracting to a magnet, and they start to, wherever they end up to stay, those magnets, they color code these three. So one of those pendulums is blue, one is red, one is green. And the places that they are just stopped, they are having these colors. And you see that there are different shapes you can create, you can get by changing the initial condition. I mean, where you release the first magnet. And this is the definition, in fact, of the chaotic behavior, that with initial condition, it changes the final outcome. And when the systems are closed, means that the energy, they don't exchange energy with the environment, this initial condition doesn't change. But the many things in nature, the system is open. So initial condition changes means that you will have so different, the final outcome would be so different. So I'm unpredictable. But the thing that Mandelbrot did and was very interesting. So he found a model that unveiled something which was invisible. And what here was invisible was these patterns. And that is what we want to do in the science. We want to show the patterns, show the processes. These are the things which is really invisible. That is the one we want to show. And different methods will be used for different problems. So we did so many also graphics. They play with these functions and draw different, change the initial condition and get different patterns.
Yeah, those are amazing images. And and in some of the proposals, that you and I have worked on, we're talking about holographic images that students can immerse themselves in, which we can't show, in a 2D environment. And I want to give a thank you to Freddie, who sent stars. Thank you very much. And so this visualization and spatial thinking go together. Thinking 2D, 3D, 4D, with time. You address in your book the importance of spatial thinking in order to understand dynamic and complex systems. So a system of three magnets is a complex system. An electromagnetic field is a dynamic system. and we can talk about those in isolation, but how important is spatial thinking to, STEM disciplines, STEM careers, solving STEM problems, that we have we have problems that only STEM specialists can solve, food, water, clean air. How does spatial thinking contribute to those disciplines and solving those problems?
So there are so many studies that found that it is a high correlation between the students' spatial ability and success in sciences. Higarty is one of those leaders in the field, that she found so many very high correlation. When spatial ability has a different test, so when they take that test and then they come find a correlation with the people who succeed in sciences, or they went to get their doctoral, they have a very, very high correlation. And the spatial ability has so many different, in fact, subcategories. In general, we say spatial ability, but one is mental rotation. So students in physics, they need to shift, translate, invert, rotate in their mind, everything. And that is something that they need to have, that is skill to do that. Or they need to find information from noise. That is one special ability. Another thing is mental animation. So most of the time when they teach dynamic systems, the lecturers just show these pieces on the board or in another way, but the interrelationships, they need to create it in the mind. The pictures I showed you of fractals, the masters of the old time, they will create this in their mind. But it was until Mandelbrot, maybe 70 years ago, that he found this by using, because he was in an IBM, he was a multidisciplinary, he was in IBM, and he just put these equations in the computer, and he find these patterns. And he find the patterns for chaotic systems that people didn't know that has these patterns. So, so that was a mental animation. You need to see how they are, they come together to just see that animation. And that is also another. But with using the new technologies, we will put this more visible for students, so they could see the connections instead of making it in their mind. And this doesn't make them a less thinker, because we are hoping that by taking these barriers or stumbling blocks, we want to get to higher level of thinking to involve the students with more difficult problems. It is 100 years, our books, it hasn't changed with the 100 years ago. I think if we are going forward, every year our books, not every year, but at least every 10 years, our books should represent harder problems, not we just solve the same problems every year.
Yeah, thank you. So I want to say hello to folks who have joined us from the Netherlands. If you hear noise in my background, I'm in the middle of a construction zone in my own home. So, but have earbuds, will communicate. So if anybody has any questions they want to ask Mojgan, feel free to post those in the chat, and our crack team behind the scenes will get those questions to us. And hello to folks from Indiana. So also in your book, you mentioned, the difference between how novice thinking and expert thinking. So in education systems, in education, we know that a novice to the field thinks differently, sees things differently than the expert. And can you talk a little bit about how visualization will help get those learners from novice thinking to expert thinking, and give a physics example if you can?
It is very interesting that the psychometric, that the people who measure the spatial ability, they just did their research, and the people in physics education, they did research. But if you look at them and compare them, and I compared in this book, you will see that they converge. This is like the same thing. They find the same result. And one of those things is that um, um, physics educators who has done research on students, they call it ontologies. So Novice tend to categorize everything based on category of matter base, because matter is most tangible. So there are so many things like processes, like energy, heat, waves, current, electric current. These are processes. But when the students don't categorize them on the processes, they categorize them like a substance based. They treat it as their substance, so they can never understand that. And this is also the same thing you will see that in the spatial ability, that when the students want to, they find that have a special ability of finding the mental animation of the processes. So, and then there is another way I think is that during the year, as the science evolved, the people's mind has evolved. They went from static thinking to dynamic thinking to probabilistic thinking. So students, they are in that static thinking and they need to come to this dynamic thinking. And all of this is need the special ability of a skill behind it. And what we are using in a visualization to answer your question is to see those connections, make those connections visible. So we have the telescopes to see far, we have microscopes to see tiny things, but we don't have a tool to see the relations. And when the students see those things, they could understand and come from moving from that ontology, building a type of thinking that is more probabilistic, more, in fact, dynamic, and they can see that as abstract processes. If you ask any professors, they see that energy is the hardest topic to teach because it is process-based, or heat.
And certainly solving energy problems, global warming problems, clean water, all of those are complex systems, and we have to be able to visualize them in order to understand them, in order to move forward and solve those big problems. Is that true? Yeah. So, hey, send us some stars. Send us some love out there. Greetings to the folks in Indiana. Greetings to our friends in Canada. If you have questions you'd like to ask, please post those. I'd like to remind everybody that the SETI Institute is a nonprofit science research institute that conducts education and outreach, and programs like this really rely upon our friends like you. So just remember to visit SETI.org. And if you can, be sure and donate and help out the Institute. The Institute takes science communication seriously. Here we are on SETI Talks, and we have a SETI Live program, we have publications. Can you talk about a couple of systems that we could approach differently in our scientific communication, by using visualization? How can we improve our communication skills and practices using visualization?
So SETI Institute is about astrobiology mostly. So you have so much astrobiology research. So astrobiology, the biology is all about fractals and systems. So one of the applications of these chaotic systems, when you visualize it, it is to find the biological textures, to just make those in different projects to see how this biological system, when you change the initial conditions, how they will end up, and in the projects, in the using technologies. So I think that is one applications, but the applications of systems is everywhere, and we need to see that when we want to teach. That is what type of systems we are teaching to students, and look at what type of cognitive processing needs. And the curriculum developers also need to think about that, what type of cognitive process we want to, is like a skeleton of that curriculum, that what is you want to convey and what special skills. And based on that, find the technology or find the, not just technology, experiment, demonstrations, anything that it can make that clear.
Yeah, thank you. I'm looking for questions. In the meantime, I'll mention that one of our communication vehicles is the SETI Talk, which is an hour-long, small panel presentation that registration is required. The next SETI Talk is November 17th, and it is on UAPs. There will be a link to the registration, and you can always find information about SETI Talks on our website. So we're coming up at the top of the hour, Mojigan. So I think I'll pose my last question to you, or the last question. What do you want to do next?
Next, I want to create as many as experiments to make these things that was invisible, visible, hopefully in a large scale for different physics problems, physics, different fields of physics.
Okay. And as your colleague, I'm looking forward to some success in your proposal writing, because you'll bring some really new and exciting work to the Institute. I want to say hello to our friends that are listening in Denmark. To everyone, send us some more stars. Please remember, we're a small nonprofit science research institute. Visit SETI.org on how you can get involved. And we'll say thank you and have a good, one question. We have a question from Ivar. How are fractals helping visualize relationships between entities?
Fractals, in fact, show the patterns. So, in fact, they define that pattern. So when you have the differential equation, so the differential equation, it shows how the system or your variable, it depends on your variable, on your function. But for the fractals, it is like a self-similarities because you are finding iterations. So you have the functions, the function have, you put a variable in the function and you feed the variable again to the function, the answer, and you repeat that again and again. So it is different types of dynamicity here. Instead of putting the time there, you just repeat the process. Every time you feed the outcome again to the function, and you find those patterns of similarities. So then these patterns of similarities you can find in the trees, for example, in landscapes, in beehives. So you, as you find those patterns, you can find those structure, the biological structure, the skin, everywhere you can find those patterns of self-similarities.
Okay, unmute. We have another question, and this one's from Sean. How would Dr. Haganekar represent complex flow patterns such as turbulence or laminar flow over a complex surface?
So laminar flow is also can be determined by the differential equation, but I had an example in my book on about the flow pattern, the turbulent flow, like we have the pattern of like a candle and the turbulence that happens in the air around the candle. And there were the ways researched, I saw a thesis on this, that there is a method to find, in fact, they inject some, what they call it, something to track the motion of the airflow. So they can track those motion and they can find the pattern of those, they find the equation of the motion. And maybe it's not fractal, but it is a chaotic. It is a chaotic behavior. So not all the chaotic things are fractals.
Fractals, yeah. But if I can add, to your response, there's many ways to visualize. There's fractals, there's AR and VR, which can be immersive holographic visualizations. There's, you in your book, you detail different technologies that can be employed to visualize different systems. And I'll just say there's the book. And I think one of Beth or Rebecca will put a link in the chat for those of you who might be interested in her book. I want to thank Melissa for her stars. Thank you. And I'm watching. I don't see any more questions. And I'm waiting. So I'll say thank you, Mojgan, and thank you, Jasmine, Rebecca, and Beth for working in the background to make this happen. And thank you for everyone for joining us.
Thank you so much for having me.
Yep. Visit us at SETI.org.
Thank you. Thank you, everyone.